Hi everyone, this is Tong from University of Florida, and today I'm going to give you a presentation of the project in the class Network Science and Application. My project's title is Graph-Based Canonical Image Selection and its application in image set compression. The presentation is divided into 5 parts. First, I will introduce the background of this topic, then is the related work. After that, I will explain the proposed scheme and also the experimental results and the conclusion. Now let's come to the first part. In recent years, canonical images are very important in many scenarios. For example, in video summarization, we select some canonical images, in other words, the keyframes, to summarize a video. And in other applications like image set compression or image search thumbnails, we can also find representative images from a very large database so that the user will have a direct impression on the database very quickly. There are two classes of related work. The first is targeting the video summarization. Basically, they use a user attention model. This is actually a multimodal, including motion attention, face attention, camera attention, and so on. For each model, they define a template and find those keyframes or representative frames for each category. And another class is called canonical images in an image set. Those sets consist of similar images of one object, such as the images for the Statue of Liberty. And there are three kinds of related methods. The first one is called metadata-driven approach. Basically, it estimates the viewpoints of each image and select those views with a very good geolocation and angle. The second kind of approach is called visual content clustering. They extract local feature and color histogram of each image. Then they perform a k-means clustering to find the represented images. Those images are defined as the clustering center. This is effective, but the user need to decide how many cluster there should be. So this is not very flexible. The third one is called visual word distribution. This is similar to the text processing. They define a TF-IDF parameter, and they use this one to rank the images. This method is better than the previous two, but it still fails to consider the visual word's importance in different images. So in our scheme, the graph-based canonical image selection, the intuition behind this idea is that we assume people tend to view a local feature and other features in the neighborhood first, not the entire image at once. So furthermore, we assume that canonical images contain the largest quantity and the most important visual words. Based on this idea, we design a scheme that contains three major steps. The first is called visual word importance and ranking. The second is called image similarity and ranking. The third one is called set coverage method, and we use this method to select canonical images. Now let's come to the first part, the visual word importance and ranking. In this step, we design a 4-layer graph, and this graph, the first layer is the visual word. It's linked to the second layer, the image, And the third layer is called MSER, maximally stable extremal regions. This is very similar to the saliency map or region of interest, which is the most important part in an image that contains the most important visual word. And the fourth layer is another visual word. Through this model, visual words and images are linked. Then we can define the visual word similarity in this equation. In this equation, M is all visual words in the MSER, and this is PVJ condition M is the normalized term frequency of the visual word VJ and in M, and PM condition I is the normalized MSER frequency in the image I, and Pi condition V sub I is the inverse image frequency of the visual word V sub I in image I. And after we get this visual word similarity definition, we use the page rank algorithm to rank those visual word and get the visual word importance ranking. The visual word importance can be written in this form. W is the normalized visual word similarity. P is a distracting vector for random work behavior, and D is a constant damping factor. So we use PageRank algorithm to solve this equation and get the visual word importance. The second step is called image similarity and ranking. This is very similar to the first step. We construct a three-layer graph in this step. The first layer is the image, the second layer is the visual word, and the third layer is another image. In our experiment, the visual word is the quantization of saved local features. Then we can define image similarity through this equation. In this equation, Pi sub j condition V is the inverse image frequency of visual word V for image I sub j. And the probability V condition I sub I is the normalized term frequency of visual word V in image I sub I. And VIV is the visual word importance of V, and N is the number of features in image I sub j. After this, we perform a very similar procedure, which is the PageRank algorithm to rank the image similarity, and we find the top K rank candidates as the image candidates for the final step to select the canonical images. And it's worth mentioning that because in this equation we used the visual word importance defined in the previous step. So through those two graphs, the image similarity and the visual similarity are defined and linked together. The third step is set coverage method, and in this, as we explained before, in step 2, we use image importance to find the largest quantity, and in step 1, we use the visual word importance to find the most important visual words. Then we define this omega I, and in this equation, G is the current selected canonical image set, and this is the set of visual words that only appear in image I sub I instead of any other image in G, and this is the number of visual words covered by I sub I. Then the set coverage method is like this. First, G equals to it contains no elements, and then we select an image I sub I in a set that maximize this omega, and then we add I sub I to the G one by one. If there is a certain number of canonical images I selected, we will stop. Otherwise, we will repeat to the second step. In this manner, we can find the most important one, or in other words, the most representative or most canonical image first. And in this sequential procedure, we can find the best canonical images we want. We perform experiments on the data set called Colossum. This dataset contains the same building Colossum, and it has 500 web images. This is the top 5 results. We can see that those 5 results are very representative, and also it contains different views. And to further evaluate the efficiency of this method, we implement it into our image set compression scheme. This is the image set compression. The problem here is to compress the image set jointly, and we can exploit the redundancy between those similar images. Basically, we use for those canonical images, we compress them independently, and for others, we can reference those canonical images use a 3D model, and we can compare this scheme with the random reference selection. It's very obvious that if you can select very representative and very high quality canonical images as reference, other images will have very good reference frames so that we can compress them very efficiently. We test them on the dataset Notre Dame. It contains 714 images, and from this curve, we can see that with canonical image selection, there is about 10% compression efficiency improvement over the random reference selection. This is a very good proof that the canonical image selection method we design is very efficient. Finally, let's come to the conclusion part. In this presentation, we propose a graph-based canonical image selection approach to select the subset of photos that best summarize the photo collection. And on dataset Colossum, it selects canonical images which are very representative and also of different views. And we also implement the image set compression. And by providing canonical images as high-quality references, our graph-based method improves compression efficiency by about 10%. And of course, there is still room to improve. For example, we can further perform further subjective experiments to give us a better proof. This is the end of the slides. Now let me briefly introduce the codes I use. For the local feature extraction, I directly use David Law's SIFT feature detector. The MSER code could be found on the internet. The MSER code is an open source code, and this is Panorama Notre Dame. This is the code for the 3D image set compression, and this image summary is the main part of this graph-based scheme. And I write a Python script to run them automatically. As you can see, they first extract SIF features and then they input MACR because MACR is very slow. So we run them and input them directly, and then we use this image summary code to ranking the image. It returns the index of different images. The first one that returned is the most representative, or the canonical image ranked first. So you can choose how many canonical images you want from 1 to 100 or any number you define. So this is basically the end of my presentation. Thanks for watching.